Hello and welcome to this podcast on business innovation through new technologies. Today, we are diving into a very essential topic, the foundations of wireless technologies, which play a crucial role in modern communication. Wireless technologies enable seamless connectivity, powering everything from mobile networks and Wi-Fi to IoT devices and satellite communications, shaping how we interact with the digital world. Let us overview the key concepts including wireless spectrums, modulation techniques, and standardizing bodies. The current podcast is created by Jitendra Tomar, an academician and experienced training consultant passionate about knowledge sharing and skill development. With years of expertise in education and corporate training, the intention is to bring insightful discussions and valuable perspectives to the audience through podcasts. This podcast is designed at JT Design Studio, a creative hub committed to producing high-quality, engaging, and educational content that resonates with learners and professionals alike. Let us start by understanding what wireless technology is. Wireless communication transmits data without physical cables, using electromagnetic waves for seamless connectivity. It enables devices like smartphones, IoT sensors, and satellites to communicate efficiently, supporting mobility and scalability. By utilizing various frequency bands and transmission techniques, it ensures fast, reliable, and secure data exchange in today's digital world. Let us dive into the key concepts of wireless technology. Towards end of the podcast, we will also cover various generations of wireless technology along with their corresponding standards. The first key concept that we focus on is the radio frequency RF spectrum. The radio frequency RF spectrum is a range of electromagnetic wave frequencies used for wireless communication, including Wi-Fi, Bluetooth, radio, and cellular networks. Each type of wireless technology operates within a designated frequency band to prevent interference and ensure efficient communication. For example, Wi-Fi typically operates on the 2.4 GHz and 5 GHz bands, while cellular networks use multiple bands from low megahertz to high gigahertz ranges to balance coverage and speed. These bands are regulated to prevent interference. Regulation ensures reliable communication. Regulatory bodies such as the FCC in the US, ITU internationally, and national telecom authorities manage RF spectrum allocation, ensuring that frequencies are efficiently distributed among different industries. Without proper regulation, overlapping signals could lead to congestion, interference, and degraded network performance. The next key concept covers modulation techniques. Modulation techniques allow data to be transmitted over radio waves by modifying a carrier signal. These methods enable efficient communication by ensuring signals can travel long distances and resist interference. These techniques are methods used to encode digital signals onto carrier waves. Examples include AM, FM, and QAM. The first modulation technique is amplitude modulation AM. It varies the amplitude of the carrier wave. In AM, the strength, that is, the amplitude of the carrier wave changes based on the input signal while the frequency remains constant. It is commonly used in AM radio broadcasting but is more susceptible to noise and interference. The second modulation technique is frequency modulation FM. It varies the frequency of the carrier wave. FM adjusts the frequency of the carrier wave according to the input signal while maintaining a constant amplitude. It provides better sound quality and resistance to noise compared to AM and is widely used in FM radio, two-way radio communications, and TV broadcasting. And the third modulation technique is quadrature amplitude modulation QAM. This technique modulates both amplitude and phase. QAM combines amplitude and phase modulation to transmit more data over the same bandwidth, making it highly efficient. It is commonly used in digital television, broadband internet, and modern wireless communication systems, for example, 4G and 5G networks to enhance data rates. The next concept that we intend to cover is multiple access techniques. Multiple access techniques allow multiple users to share the same communication channel efficiently. These techniques help maximize bandwidth utilization, reduce interference, and ensure seamless connectivity in wireless networks. Let us explore various access techniques. The first technique is Frequency Division Multiple Access, FDMA. It assigns separate frequencies to different users. Each user is allocated a dedicated frequency band for communication, preventing interference. This technique was widely used in 1G analog cellular networks and traditional radio communications but is less efficient for high-capacity networks. The second technique is TDMA, which stands for Time Division Multiple Access. It assigns different time slots within the same frequency. Users share the same frequency but transmit data in predefined time slots to avoid overlapping. TDMA was commonly used in 2G, GSM networks and remains relevant in some communication systems due to its efficient time-based allocation. The third technique is Code Division Multiple Access, CDMA, which uses unique codes for each user to share the same frequency. Each user is assigned a unique code that allows multiple signals to coexist on the same frequency without interference. CDMA was a key technology in 3G networks, improving capacity and security over previous methods. And the last technique to be discussed is Orthogonal Frequency Division Multiple Access, OFDMA. This technique improves efficiency in modern wireless networks and is used in 4G and 5G networks. OFDMA divides the frequency spectrum into multiple subcarriers, allowing simultaneous data transmission to multiple users. It enhances network speed, efficiency, and scalability, making it the preferred technique for 4G LTE and 5G networks. The next topic that we will discuss is wireless standards bodies. Wireless communication relies on globally recognized standards to ensure interoperability, security, and efficiency. Various organizations establish and regulate these standards to support seamless communication across different devices and networks. The first establishment is IEEE, which is an institute of electrical and electronics engineers, and defines Wi-Fi and other wireless standards. IEEE is a leading organization that develops technical standards for wireless communication, including Wi-Fi 802.11 standards, Bluetooth, and Ethernet. These standards help ensure compatibility between devices and improve wireless performance. The second establishment is Third Generation Partnership Project, 3GPP. It defines mobile network standards. 3GPP is responsible for developing the technical specifications for cellular networks, including 3G UMTS, 4G LTE, and 5G technologies. It plays a crucial role in defining protocols for mobile communication, ensuring global connectivity. The third setup is International Telecommunication Union, ITU. It is a specialized United Nations agency that oversees radio spectrum allocation, satellite communications, and international telecommunication policies. It ensures harmonization of frequency bands and promotes cooperation between countries for seamless global communication. Let us now delve into different generations of wireless technologies and their corresponding standards. Wireless communication has evolved significantly over the decades, transitioning from basic analog voice services to high-speed, ultra-low latency networks supporting modern applications like the Internet of Things and real-time communication. Following is a breakdown of the key features of each generation. 1G, the first generation, started in 1980s. The first generation of wireless technology introduced analog voice communication, enabling basic mobile phone calls. However, it had low speed of around 2.4 kbps, lacked encryption, and was highly prone to interference. Standards such as AMPS, NMT, and TACS were used during this era. The next is 2G, the digital revolution, starting from 1990s. With the introduction of 2G, mobile communication shifted from analog to digital, improving security and enabling services like SMS messaging. It offered higher speeds, around 50 kbps to 100 kbps, and was based on standards like GSM, CDMA, GPRS, and EDGE. This generation laid the foundation for mobile data usage. Following the previous is 3G, the era of mobile internet, started in 2000s. The third generation, 3G, introduced mobile internet and video calling, revolutionizing how people accessed information. With speeds reaching 2 Mbps, users could browse the web, send multimedia messages, and stream content. It was based on standards like UMTS, HSPA, and AVDO. The next upgrade was 4G, high-speed connectivity in 2010s. With 4G, mobile networks became faster and more efficient, offering speeds between 100 Mbps to 1 Gbps. It enabled HD video streaming, voice over LTE Vault, and reduced latency, making mobile applications more seamless. The most widely used standards were LTA and LTAA. The next is 5G, the future of connectivity in 2020s and beyond. The latest generation, 5G, offers ultra-high speeds from 1 to 10 Gbps, ultra-low latency, and the ability to connect millions of devices simultaneously. It is essential for applications such as smart cities, IoT, autonomous vehicles, and real-time cloud gaming. The standard governing this generation is 5G NR, that is 5G New Radio. Each generation has played a crucial role in shaping modern communication, with 5G paving the way for next-generation innovations. The consolidated table is presented here for the ready reference of the learners. Towards end of this podcast, let us also look into the future trends in wireless communication beyond 5G and the rise of 6G. As wireless technology advances beyond 5G, researchers and industry leaders are working on next-generation innovations that will redefine connectivity, speed, and efficiency. These advancements aim to support ultra-fast data transfer, intelligent network management, and global coverage, paving the way for new applications in healthcare, smart cities, autonomous systems, and beyond. Some key future trends include terahertz communication. This revolutionary technology explores the terahertz frequency spectrum to achieve ultra-high-speed data transfer, reaching speeds in the terabit per second (Tbps) range. THZ communication will support high-resolution imaging, immersive virtual reality, and advanced medical diagnostics. AI-driven networks. Artificial intelligence will transform network operations by automating traffic management, predicting network congestion, and optimizing bandwidth allocation in real time. AI-powered wireless networks will enhance security, energy efficiency, and user experience across various applications. And the third is satellite-based internet. Companies like Starlink, OneWeb, and Amazon Kuiper are launching low Earth orbit satellites to deliver high-speed, low-latency internet worldwide. This innovation will provide connectivity in remote and underserved areas, improving communication for rural communities, disaster relief efforts, and global businesses. We come to the end of this podcast on business innovation through new technologies, where we explored the foundations of wireless technologies. Thank you for being a part of the Knowledge series. Please remember, learning always is an art for scholars and is a lifelong activity. Hope to be with you in some other session, some other time. For more academic content on various subjects, remain connected.